So if we look at number 11, I'm just going to kind of sketch real quick what I saw there. And let me know if I made a mistake, please. So I saw... And I don't know what the speed was. 10? All right, so this is our problem. We want to know what the speed of the car is when they make it to state 2 of the problem. I'm going to make this state 1 of the problem. Fair enough? If this is a conservation of energy problem, and I see all the hallmark signs that it is, things like I'm asked to find a velocity, I see a picture where there's a clear change in the height of the object, yet I also see a picture in which the track or the path that the car takes is curved in such a way that I could not use forces to figure this out, because the direction of any forces acting on the car is changing all the time. So that's one reason why I know I can't use forces to figure this out. But I probably could use energy. Now, in order to do an energy problem, I have to kind of establish what I'm going to call my baseline for this problem, or my reference level. There is a clear reference level that's given to me. I could use that reference level if you choose. So you guys who asked, do you want me to use the reference level that's given in the problem? That would be this as being 0 for the height. Does that work out? All right. So they would like to know how fast the car is going when it makes it to state 2, suggesting that there is kinetic energy at state 2. And I noticed that to get to state 2, I will have to be above the reference level, so there's gravitational potential energy there as well. At state 1, I clearly have kinetic energy because they told me the car's velocity is 10, and I am above the established reference level, so I have gravitational potential energy as well. Now, I need to ask myself if I think these two things are equal to each other. Was there anything in the problem that suggested that something was taking energy out of the system? No. There probably actually is. And we will talk about a real version of this problem right after this one. I'll do a little bit of inline teaching with new material. But right now, I think we are supposed to assume that the energies are equal. So although they gave me the mass of the car, that was actually an unnecessary piece of information. But let's go ahead and move on. 1/2 mv squared plus m. It's a book problem, so you should put 9.8 here if you want the answer in the back of the book. But you know me, I don't care. I don't need the book to prove me, to validate me. So I'm using 10. On the other side, m times 10 times 15 plus 1/2 mv squared. That's probably enough. So you guys who were looking for number 11, would you agree?
If you use 10, you get 0 energy because for some reason, but if you use 9.8, you get the right answer. So 10 cancels both sides of it out because of how it. So it would be confusing to use 10 because of the density you get.
Confusing to you.
Well, what I mean is I got 0 on my.
Okay, so the velocity of the car is 0.
Well, if you use 9.8, you get the answer that you got.
So it indicates that our plane is traveling at some velocity when it lands, and then it contacts the tail hook, but I'm not going to draw it like that. There's a lot of conversations to say that it presses up against the spring, and it reduces the spring to a certain distance. They do not use springs to stop the planes, so they don't. They use a steam mechanism that launches the planes to allow the planes not to be jerked backwards when the plane stops, which would be bad for the planes being flung back into the ocean. So they don't use a spring system to stop the plane, but they do use an energy reduction system to reduce the energy of the plane. But we're told it's a spring. And considering that when the plane hits the spring and compresses the spring, it comes to rest, it looks like at this state, we will have nothing but elastic potential energy stored in the spring. And we are only to consider the fact that the plane is landing on level ground and is already, or level surface, and is already on that surface. So I would assume that means that we have all kinetic energy at the start of this problem. Assuming there is no losses due to air resistance or friction, then we could probably set these two things equal to each other. And I think that's really all I need to say about this question, because we won't run into the the nasty 9.8 problem here. That could vex some of you. Is that enough for the person who asked about number 20? Or should I continue? Okay. So when I pull this back against the spring, I'm clearly storing elastic potential energy here. However, how would you like to handle the gravitational potential energy in this problem? Would you like to only worry about comparing these two things together? And if so, then we can make the car currently on the established level for gravity and say that there's no gravitational potential. Or do you want to anticipate a further portion in the problem where the cars are going to have to return to this level and make this the established level for potential energy? Makes no difference because they don't ask what you need in question A for going down to where the cars will eventually be. They only ask about making it to the top of the first hill. But if you want, you can still establish your reference level to be wherever you'd like. So whoever asked about this problem, where would you like to establish the reference level? There's fine for me. So if I establish the reference level to be right here, then by doing a little bit of arithmetic, I realize that we are 5 meters above the established reference level. There are plenty of roller coasters that do this, who have their loading tower at a distance that is higher than the lowest point in the ride. It's just a way of giving them a little extra speed later on in the ride. Also, it's usually for aesthetics for where they place the roller coaster on the geography of the land. So that means I would have elastic potential plus gravitational potential at the start of this ride. But it also means that when I'm at state 2, I will have gravitational potential at state 2. The real question comes down to, is the car moving at state 2, or am I looking at the amount of energy just to get it to the top of the ride? My understanding is that I just need to get it to the top of the ride. Is that right? Yes, ma'am.
So it depends on how they ask you the question.
Probably. When I'm looking at it, they ask what the minimum distance I have to pull back, or no, the minimum spring constant necessary to just make it to the top of the ride. So they're looking at just enough energy to get me here. So, I mean, truthfully, I'd probably want to have a little kinetic energy up there, but this might be very little. And if you're moving at 1/10 of a meter per second, do you really have any kinetic energy? Well, not compared to being 15 meters off the ground. You follow what I'm saying? So, but yeah, I think the idea is minimum means that you have to get up there. They didn't say you had to stay up there. Is that good? All right. So this will not actually get you the answer, by the way. And this is one where that pesky 9.8 will rear its ugly, ugly head. So I want to make sure I address that. So I'll put the 9.8s in there because it doesn't matter to me. I'm not going to do any calculating. I only see one unknown here. I can find K, but this will not be the answer. If you want the answer, the actual value for K actual, is going to be 1.1 times the K you get here. They say for safety purposes, we want spring constant to be a little bit larger than this. So it will actually go over the top. So we're finding the minimum when we find K, but the actual one is supposed to be 10% greater. So you multiply it by 10% or 1.1 to get an additional 10%. And that way you can get the actual answer at the back of the book. Question so far? Now be careful here. They say to use this spring constant to figure out how fast you'll be going at state 3. But they also reduce the occupancy of the car from 400 kilograms to 350 kilograms. So they're going to be going faster than the people would have been if they were 400 kilograms because they'll be going slower. There's less energy, right? Same amount of energy to spring, but less mass of people. There it is. So with them having less inertia, they'll probably be going faster here than they would be if they were 400 kilograms, which is why you don't actually build roller coasters using springs. You don't want it to be dependent on the mass of the people in the ride. So you use a different system, because if it's dependent on the mass of the people in the ride, then every ride is different. That's bad from an engineering standpoint. Follow me? Okay. Question number 44 has a ski launch. And I don't have the numbers in my head, but whoever asked about this probably does. So it looks something like this. And they say that this is 60 degrees, and they say that the arc from here to here is 90 degrees, which means this is 30 degrees. So there, did a little math. I would expect you guys can do that math. Maybe not. I don't know. And the person starts up here at the top of the ski lift, and it's going to come here, and they're going to jump. Good? What is this height? Because I don't remember. 25 meters, perhaps? And is the height here 3 meters? So they're asking for how, they're really not asking for how fast they're going at the bottom of the jump. They're asking for where the person lands. That's a projectile problem, and I am not doing this projectile problem. You can do it. You need to find the range, which means you'll need to make a vertical and a horizontal, and you'll have to remember that Vy naught is going to be V sine theta, and Vx is going to be V cosine theta, and you can do all of that garbage. Delta Y in this one is minus 3 meters. You do that. I am not doing that. We have passed this section, and it's not very fun, okay? I'll get you to the point where you can figure out this velocity. That's the part I'll do. Is that okay? So I don't know who asked, but that's the only part I'm going to do. You have to do the projectile problem. You're not going to get me to do that for you. But I will say that here, if I set this as my reference level, the ground, then I have gravitational potential here at the start. And at state 2, I'll have gravitational potential plus kinetic. Yeah, if you want the answer in the back of the book, you better use 9.8. And you better use 9.8 here if you want the answer in the back of the book as well. But I'm not really interested in the back of the book. What you can't do is you can't use energy to figure out where the person lands. This part of the problem, you only have projectile motion and using motion equations. There's nothing else you can do there. There's no shortcut. It's all long. So I'm not really going to go into it too much. I do want to talk about this question, however. So if this answers whatever your question was, I'd like to move on. If it doesn't, please help me identify where the weakness is, and I'll continue to speak to it. Appropriate wait time is 3 seconds. I gave 7. So I think I'm okay. For just a brief moment, using gravity as 10, we're going to have m times 10 times 25 equals m times 10 times 3 plus 1/2 mv squared. How fast are they launched? You guys have calculators. Make this happen. Compute this stuff. 250 minus 30 is 220, square root of 440. It's not much here. Yes, sir. 21 meters per second. Now, this made an assumption. And the assumption was that there was no loss due to friction or air resistance. So what if you're actually on site and your friend is doing the jumping and you observe them doing the jumping, and you find that when they're only launched at 15 meters per second. Now you'll notice that 15 meters per second is clearly less than 21 meters per second. Would you correctly identify that something did work on the system? Could you calculate how much work was done on the system? I said could. Would you please, in this moment, calculate how much work was done on the system? I want to know if you know what I'm asking. Again, the information that you're missing is that they are 60 kilograms. But that's the only information that you're missing in order to complete the task I've assigned. Now, for those of you who don't know what the task is I've assigned and are having some difficulty doing this, please listen carefully. We were given the amount of information, we were given the amount of energy the system had at the start. We were told how high the person started. So we know how much gravitational potential energy there is at the start of this problem. We also know that when they reach the bottom, we know how much gravitational potential energy they must have because they are still 3 meters above the ground. In addition, we expected them to be traveling at 21 meters per second, but on further inspection, we find that they're only traveling 15 meters per second. That's clearly less kinetic energy than we expected here. These two things are not equal. That part should be self-evident, that if they get there and they're traveling slower, then there's less kinetic energy because nothing else has changed. The shape and size of the ride isn't any different than it was before, but we expected them to be going one speed and they're going another. Well, and let me be really clear, these are the notes for today. This is the teachable moment I was telling you about. Because this shows up in like 3 other problems in your homework as well. Work was done by friction, but you can't calculate that work using any means that we've talked about so far. What I mean by that is you can't say, okay, well, work is force times distance times the cosine of the angle. Yeah, there's a lot of angles there, but look, this whole thing is curved, which means the normal force is changing, and not necessarily in a uniform, regular way. Although it is circular, I don't think you have a means by which you can calculate the work done traveling through the circular portion of the track. Not to mention the least of which is, I never gave you mu, which would be necessary to calculate the force acting on them. But you don't need it. You see, one of the things I'm trying to get you to understand is that if energy is conserved, then knowing that this side is greater than this side, that means some energy disappeared. Well, the likely place that that energy disappeared was work done by friction. That was the most likely place that we lost energy. That missing energy. Now, I've been teaching this particular topic for a long time, and there's a lot of different ways I'm supposed to talk about this. This is the way I've settled on. And the reason I like this method, when it deals with a amount of work that can't be identified directly, I mean, I can't use the equations for work to do, is that we know that this occurred during the time that the person was traveling from state 1 to state 2. So they had this energy at state 1, but the environment has this energy once we make it to state 2. I like the idea that we are accounting for all the energy, and I like the idea that you never have to worry about making energy negative. There are alternatives to how this can be taught, where you do this differently. You guys who might have been in AP Physics 1 last year and used the Actina book, you know that they're a big fan of those bar graphs, with the work being in the middle of the bar graph. And if it's a positive work, it's on top and it's adding. If it's bottom, it's taking away. I hate the stupid bar graphs. They don't really mean anything. There's also a group of people who teach this where they place the work done on top of the equal sign to indicate that there's not an equal sign, but like an arrow here. And work was done going from one state to the next, and you add it when the work is being added to the system, or you subtract it if it's being taken away from. I don't like this one either. I tend to be pretty much a pragmatist, which means we started with this. We still have this. We just have to account for all of it. That's how I feel about it. There's several alternatives for me to explain it. This is the one I'm going to use. If you have a method that already works for you or you feel comfortable using, that's fine. It all works out to be the same anyways. So any other method that you use here, you're still going to calculate the same. You're still taking a look at how much energy you had, how much energy you have, and how much is missing. That's still what it comes down to, accounting for all the energy. Questions? This was not the question in the problem. I'm adding it because it's important. All right. Let me start by saying that this is an energy question, sure. And there's a lot to it. Elastic potential energy here. The box makes it to the edge of this ramp probably with a lot of kinetic energy, still on the lowest level of the problem though. It's going to travel along this ramp where there's a coefficient of friction of 0.2. And when it makes it up here, the box is going to have, hopefully, gravitational potential energy and kinetic energy. You guys all agree with that statement? Everything good? Now, here's the thing. The problem does have a follow-up. And the big thing here is that you need to know how fast the box is going. That's what this problem is really about. If you want to do the projectile problem, you need to know the projectile information, which is velocity. This part of the problem, though, is not interesting. In fact, there's a single equation that if you memorized it, you can do it in one piece. Right? The range equation, this object is being launched and landed at the same height. Think back to projectiles, we had this. I don't use it often, but this is true because delta y equals 0. You need this velocity to give you the angle. It's like 30 degrees. No, 45 degrees. So that part's not the hard part. Getting velocity, that's the hard part. So I'm kind of ignoring the projectile portion, if that's okay, because once you have the projectile portion, we've done that already. The reason I want to talk about this problem is I could speak to this problem like a work energy problem. I'm saying that because energy is not conserved from here to here. I said to you before, there's going to be less energy because as the block goes up the ramp, it loses energy. But unlike the last question, which told us how much energy we had at the top, we have to figure out how much work was done. And not just by friction. You see, the problem with this question is that truthfully, the way I should do it is once I have the kinetic energy here, I should use the work energy theorem to figure out how much energy is lost while it goes up the ramp. Because the block loses energy because of friction, but it also loses energy because of gravity. That's just the thing. Now, if you're real shrewd, you'll know that this is supposed to equal minus the change in potential energy. We talked about that 2 days ago. But let's say we don't. Let's say all we remember is what we talked about before Thanksgiving. Well, that would mean this is going to be friction times d. I don't know what this length is, so I'm just going to put d. Is that okay? Friction times d times the cosine of 180 degrees. Work done by gravity? I don't know. I have 2 ways to do that. If I think about my free body diagram, remember it's mg, normal, friction. And the box is going that way. So do I want to deal with the component of weight down the ramp? Is that how you want to do this problem? If so, then it would be mg sine 45 times d times the cosine of 180 degrees. We've done this before. This is in your notes, or should be. If you don't want to deal with the component of the weight, and I don't, I want to just deal with the weight, then you could do this as mg times d times the cosine of the angle between the displacement and mg, which is 135 degrees. You get the same answer, right? You've done this, you get the same answer. Sine of 45 and cosine of 135 are the same numerical number. Numerical number, that's probably stupid of me to say. And the cosine of 180 will make it negative, so that the cosine of 130 comes out to be negative. These have to be negative because they're taking energy away from the box, kinetic energy. And that's how you can figure out the energy at the top. I don't like doing it this way, but this way you've been taught. We've talked about this before. You might not remember it, but we've talked about it before. So you could have broken the problem up here to figure out how fast it's going, and then using the work energy theorem gone up to here. But you're wondering why Mr. Shelton assigned this problem to you during conservation of energy? Well, that's why it's in the additional problem section. There's other ways to do this problem. I could, instead of doing it the way I just described, I could all this out of the way, realize that I have two states of the problem. The bottom state, I've got kinetic energy. Actually, I could go back even further. Two states of the problem. No energy lost between when it's launched here and makes it to the ramp. So start here, 1/2 kx squared. Set that equal to mgh, got to figure out what h is, how high it is, plus 1/2 mv squared. However, I know these aren't equal. There was still work done by friction. Now, you are not going to escape the fact that you're going to have to calculate the work done by friction. That's not going away. That's still friction times the distance times the cosine of 180 degrees, but leave that out. That just makes it negative. We make all of our values for energy positive here. We just want to know how much energy was there in friction. You do, though, have to figure out what the frictional force is. And by this time of the year, although you don't have it memorized, all of you, I would really, really like you to be moving to a place where you have got this memorized. Friction is mu times the normal force. Now on a ramp, the normal force is mg cosine theta. I'm not asking you to memorize many things. Five are the number of things I've asked you to memorize, with the most recent one being, L times 1 minus cosine theta. Now, it's still a lot. This is a lot. This problem is tough. There's a lot of pieces to it. And if you're new to physics, grapple with it a little bit. This isn't on your test next. This is a little bit higher level than I'm prepared to give you on a test. Maybe if I took away the friction, it's not. With the friction, that's a lot. It would take you 10, 15 minutes, maybe 20.